Next, we have Cadet Cappetta from United States Military Academy.
Hi, everyone. I just wanted to start off by saying thank you for coming. It's 4 p.m. on a Saturday. There's probably a bunch of other things that you could be doing, so I want to say thank you for your time. So I'm going to be talking about topological data analysis and its involvement in cybersecurity. So just a little bit of background. We all know that in our field, like we work with large data sets, and when it comes to modeling, it could be very computationally heavy. Then you spend hours coding, and next thing you know, it's 2 a.m. You're really sad. You decide you need a change in your life, and you decide to grow out a horrible mustache. And then you look yourself in the mirror, and you're like, how did I get here? Where do I go next? And my answer to you is topological data analysis. So topological data analysis involves different things. You could take two-dimensional data or multi-dimensional data. You then project it into a Euclidean space. You then do this mapper algorithm, which is also called a cover. It starts fitting points, as you can see, like trying to see what it looks like in the Euclidean space. That's how the algorithm runs. And the next thing you know, you have a graphical output. In this case, this is what a V-torus RIPS complex would look like. I'll get into that later. Another thing about topological data analysis is in some space, you expand these radii, and every time a radius touches another, it's going to create a birth along here, along the zero. And then for the first time, anytime it's not along the zero birth axis, that is when you find distinct overlap or a specific hole within it. And that tells you exactly all the information you want to know about your complex. And in this case, I'll be using a V-torus RIPS complex. With that said, is there a way to find outliers or detect that overlap in a cybersecurity data set using TDA, topological data analysis? And my goal is to do this is I'm going to use Python interfaces, using those methods to explore the data set, same ones to look at results and then formulate what's going on and talk about future work that could be from here. So why cybersecurity? I see some people have their phones, iPads, laptops, no matter where you go, like technology is abundant. I mean, you can't even eat in peace anymore, and you're doing work and you're curious, like, is my data secure? Well, the average data costs for companies, they have some incentive because it costs almost $8 million. And this was in 2018. It's gone up since then for each data breach in the United States. Beyond that, thinking about second, third order effects, like, how am I, like, what information about me is getting put out there? I mean, you could think from personal life to banking, it's important. So compromises from Google, Slack, GitHub, Uber, like they're even more costly. And so now cybersecurity is of the essence. So just a quick thing before I get into what's going on, I'm going to show you how in a topological space, a coffee mug is the exact same thing as a donut. So you take your coffee mug, in topology, you can cut things as long as you reattach them. So I'm going to cut something from the side and I'll put it in the middle. And now I have a hard top and a hard bottom as if there's nowhere to enter there. And it's still the same space. Now I'm going to start molding it. Don't think of it as glass, think of it as putty. And I'm going to keep doing that. And next thing you know, I end up with my donut. And this is topologically sound. So getting into my data exploration. So my data set that we'll be using is from the National Security Laboratory. So this is the NSO KDD data set. There's a bunch of different explanatory variables that I'm going to be using. So those vary from different or the same host server rates, as well as connections to same or different IP addresses. I'm going to be looking at the difficulty level of attack, which is also known as outcome. It's how hard is this to detect and decrypt. And so that's just known as difficulty level of attack. That's just what's been labeled. And then I'm also going to talk about certain cyber attacks. This is where topology comes into, where it becomes multidimensional now, of more than just your simple statistical regression, like what's going on. So just to quickly talk about the different kinds of attacks. You have like your denial service, remote to local, user to root probe, and then your probe. And so what I did, there were 38 attacks originally. And I was like, okay, let's simplify it down to 4 different kinds of attacks. That's how I categorized them. And so that's what's going on here. So now I'm going to talk about my methodology. Just to take 2 of those explanatory variables for a second, I chose a different server and the same server, and I analyzed what's going on. And so I just made a first scatter plot. Anyone can do that in Python. Started exploring with Seaborn, and I'm like, okay, like, is there a gradient to this? Is it heavier, where there's a server error rate different than the aggregated count where there's about 20,000 observations. And so I did that separately, combine the graphs, and I see there's excuse me. The different server actually has a lower error rate than the same server, and on the surface that doesn't really make sense. So thankfully, TDA is going to help explain this. I did some further plots, and I was like, still getting the same thing where now the outcome, it's harder to detect. So these are not just like some arbitrary thing. Now we're exploring like, these are error rates that are hard to come by. So using this, I've used the same methodology with the different explanatory variables that I mentioned about 4 slides ago. And I came to these results. This is where that persistence diagram comes in. So it took that, you can't visualize it with the technology that we have currently, but it took it into that Euclidean space, found what shapes it was around, and then it gave us these persistence diagrams. And so just for the different services and same services, the red and blue diagrams that we were looking at, I can see that there are 502 places where there's overlap with the radii. And in that V-torus RIPS complex I'm talking about that we can't visualize, that's an edge on it. And then there are 75 where it says H1, those would be holes or extreme overlap in that complex. So looking at them, they're pretty similar. But if I move on to the other attributes from this data set to explore, I see that there's as many edges as 656 and as many holes as 158, and they're different. So that tells me that there's a lot of noise going on. There's no way to statistically prove what's going on. So this is not like statistical significance based. This is very much correlation based. But building that complex will, like any, whether you do V-torus RIPS, a Church complex, or so on and so forth, you'll be able to see what's actually happening. So our results say that this has the most edges, which is the same host and the same IP address, which is something that we would want. That tells us that's the most secure. These edges mean that's the most secure, versus a different host and a different IP address tells us that it has the most holes. That's something that we wanted to believe from the beginning, but our initial data exploration told us otherwise. So these conclusions talk about, again, this is all correlation based, but the first 2 points just cover what I talked about. And then these are not simple X and Y. There's 43 other attributes that go into it. I just chose 2 specific error rates to look at. And then the rest, because it's in that Euclidean space, it takes into, so, for example, the different type of attack that's going into it. And so what's the significance of these persistence diagrams? By locating exactly where there's a birth along here. So for an error rate of 3.5, not a 3.49 or 3.51, we know exactly what other attributes are going on there. And then we can look in the data set and say, okay, compared to all these places where the birth is greater than 0, what's happening? Like, are there similar attributes? It is further than just your normal regression. So in my final slide, these are the results, again, correlation based. You can use different TDA complexes, and then building this to find more attributes or different rates to signal cyber attacks and be preemptive. That's my slide. Thank you, guys.